Today, I want to talk very specifically about physics and AI. And there's two subjects overall that I want to get into. The first topic that I want to dive into and go into very specifically is that physics is the entire process of AI overall. And I'll get into that more in depth in a second. And the second is that the physics of digital spaces do not necessarily inherit the properties and the physics of physical spaces, meaning that you need to, or people should, free their minds more when it comes to dealing with the physics of these digital spaces. And you'll find that you can start to take the wheels off when it comes to some of this experimentation. So, with that said, let's dive into that first concept that I talked about, which is that physics is in all of this. And it's common for me and to me to this day to oftentimes be in discussions with people, very smart and intelligent people, with regards towards neural networks and AI, and we'll come into subjects where we just categorize that subject as something that we don't know how it works or operates as at the moment, right? Weird behavior will occur, and then so within like hyperbolic space is a common scenario where I have lots of these discussions, right? Where I'll have discussions with lots of people, and it's like, oh yeah, just weird things happen in hyperbolic space, right? And or weird things happen with emergence. It's just you put a bunch of complex systems together, and then you get weird emergent properties out of it, right? And then so to me, I don't view weirdness in that equation, right? I don't think weirdness actually exists in that equation. I think anytime where we're putting weirdness into that equation, we don't understand the physics of that equation. But if we break it down and we simply understand the physics more in depth of that equation, then it's no longer weird. And then so within that, one of these questions that comes up a lot is what exactly is the physical storage capacity of an LLM model or an AI model? Like how much information can they actually store? And it seems like a simple problem, right? Because under physical storage limits, you would just utilize the first part of this first equation that we're looking at here, this the first law of information capacity, and these two ends. And then you can see the two ends are information capacity of the model is scaled directly by parameter size in bits of the model, which is very straightforward, right? So the very first half of this equation is exactly what we would expect, which says that if you make your model physically bigger, it physically increases the storage capacity of the model. Okay, cool. But if the equation ended there, then there'd be no more discussion, right? But we can see that there's an equals, and then there's some other variables after that equals, which means that this isn't the entirety of that equation. And so that's where this gets into, and that's where it gets kind of weird, right? Because the information capacity of an LLM model, how much information it can store, is not just related to the physical size and storage capacity of the model. It's a huge factor, as we can see. It's the first factor, right? And it linearly scales, so we can use that as kind of like a brute force mechanism. We always know that we can add more RAM to the machine, right? Adding more RAM to the machine is going to increase its information capacity and generically, but if we want to do that non-generically, we look at the right-hand side of the equation, and we can see that an actual equation comes out of this. So we have number of trained tokens times the equation within the parentheses, which is the entropy of the entire data set, minus the average cross entropy training loss. And then so this is where I want to dive into very specifically with playing around with digital physics. And then so here we'll get into, rather than diving deep into that second law of information capacity, which is a cool equation, and it's very cool, and it just stacks on each other. The bottom line, how I treat that secondary equation and these equations together, is that these are levers that you can pull, right? And then there's a lot of levers that are involved within that secondary equation. The Boltzmann constant, the Kelvin temperature of the radiator, and the merge across, like all of those factors from that first variable of the first law get factored into this as well. So there's a lot that we can play with, but to me overall, just remember that there are levers that we can pull, and you can pull these levers. You can adjust the temperature in your digital environment, which will impact the equation. As you can see here, increasing or decreasing the temperature will directly increase or decrease your storage capacity of your model, even if you're doing it in digital space, as we're going to see and demonstrate here as we go through. But diving into this, the secondary aspect of this is where I want to focus the primary portion of this video, right? So this law of information capacity, I'll leave a link to this paper, and you can read through all of their math. To me, it's very straightforward, and it's pretty proven true, right? So we can prove their math true in this next notebook and through this experimentations that we're going to go through. So what we want to do now is go into that second element that I talked about and dive deeper into that, right? Which is that we want to essentially take your mind off of the rails when it comes to these concepts, and then understand, one, that physics is at play. So number one, we understand physics is at play here. It's not weirdness, it's just understanding physics and then breaking that down. And then once we understand that, step two is physics in digital environments and in digital spaces is not the same as physics in physical spaces. And then so let's dive into that step two. So first of all, we're going to set up a few experiments to prove one of the concepts within this the paper that we were just looking at here, right? So there's a lot of that equation is a simple and innocuous looking equation, but in those two equations, but there's a lot that falls out of those equations, right? And then so those equations basically say that how these models learn is via compression, that it all boils down to compressing the data, right? That you take data and then that data has a certain value associated with it, and that's the entropy value, right? It has, all data sets will have n entropy, and that's like the max amount that it can be compressed, like the max that you can learn from the data set. And the more entropy that it has, the more that it can be squeezed. So think of it like the more knowledge that is compressed originally within the data set, the more the juice is able to squeeze, right? Like it's if it's trying to squeeze a radish as opposed to an orange, it's going to squeeze a lot more juice out of the orange, right? That's what's going on here. That's, I mean, literally the same exact concept, and that's how it's learning. Is it's compressing the data and then just compressing and shaping and transferring that compressed data, and that's essentially how knowledge, information, and knowledge progression works, right? So diving into this notebook and what we're going to be doing here today within these experiments, first thing that we're going to be doing is we're going to be looking at surge collapse dynamics and the entropy dynamics of that equation. So putting this into very simplistic terms, what that equation basically said is that we can treat this the model itself and the shape of the model itself like a jar, and then so we can essentially compress the jar, which make the jar smaller, which will make it learn better by essentially like reducing the weights, so like pruning the weights, right? So essentially what we can do, and what this is saying we should do in certain instances, and we can do in certain instances, is take our model and then let's say it's 100 million parameter model, and then we compress it. So at various points in time, we find we want to do some sort of an algorithm, right, to make sure that we're compressing the right neurons or the right parameters. But we essentially, let's say we strip out 9 million of them, and then so all of a sudden it goes from a 10 million parameter model, and then we say, boom, 1 million parameters, right? And then just compress it, shrink, prune the model. Like any sort of analogy that you can think of within that, it's just pure compression, right? That's what you're doing. You're putting it in a compression machine and then removing all of the excess. And what we're doing through that experiment alone is this, right? And then so we're showing through that. And then so that compression mechanism that we're doing in this instance, we're calling it the surge collapse mechanism. And then so the collapse, it will prune low magnitude weights below a certain sparsity threshold. It'll just randomly drop them to zero. And then we'll reduce redundancy, and we want sparsity within the environment, right? And then the surge is going to, so we shrink the weights and then we blow them back up, right? So we say you start as a 10 million parameter model, and then we're going to take like all of these excess weights, and then we're just going to set them to zero, and then we're going to shrink those out. So then like we're just going to eliminate them, and then so all of a sudden you're a 1 million parameter model. And then we're going to do surge, which means that we're going to just pump those parameters back into the model and then make it a 10 million parameter model. Again, right? So it started as a 10 million, we make it a 1 million, compress it, and then surge it. And then we do that by just injecting like random noise. So it's here's some weights, and then here's randomly adjusted weights after the surge, right? And then that's all we're doing. And then within that, what we want to do as we're experimenting with this is we want to play around and track the entropy within this environment, because that's important to that equation, right? That equation that we're looking at, it says that this compression mechanism, it's all driven by entropy. And then so our key point is that we don't want to, if we compress, when we compress, we're getting rid of entropy, right? And then so that's the trade-off that we have, is that the more we do this compression to the model, the more entropy leaves the environment, and then so that can lead to entropy collapse within the environment, which can be bad, which means that our model's not going to learn in an environment where there's entropy collapse, because it just won't explore. And then so that leads us to essentially two behaviors that occur in the model, and then two environments that occur for the model, or really three environments, right? The three environments are, it operates within a high entropy environment, that's when the weights get collapsed. We have an injection of energy in our later experiments, and then we're going to apply entropy pumps and then go into more of the digital dynamics. So keep that in mind, and I'm introducing these pumps here at this concept before we look at this code, because I want to, again, the entire concept of this, what I want you to understand at some point by the end of this is that it's all physics related, and you can take the physics off the rails. The fact that it's physics related is not an impediment. It's actually freeing, because you get the physics of digital space, and the physics of digital space are whatever you create, right? You're creating the jar. So think of the jar, right? This neural network that we're dealing with, and these concepts that we're dealing with shapes of jars and interactions by changing the shape of the jar. So with that, let's dive into what these specific experiments and what we're looking at here with this code, right? So very first thing is we're setting up our simple ReLU network exactly as I described, right? So this is all of these neural networks are very simple: input layer, hidden ReLU layer, output layer. Simple as you can get, right? And then we have our compression function, which is essentially just, again, dynamically collapsing those weights, in this instance by 50%. And then you can shrink it by whatever you want. You could shrink 90%, 80, 50, 40, 30, etc., right? And then the surge is that re-expansion, where it just brings, so we are in the compression, we're compressing by 50%, and then we're just re-inflating. And then we do that, we do a training loop off of this, and then we have our dummy data, and then so going back and tying this back to that equation, right? So what we're doing and what we're testing within this instance is, so we have our dummy data set, and then what we can't control this is a set variable, right? This dummy data set that we're introducing, remember, a huge part of the equation is whatever the set entropy is of this. And then so whatever the set entropy is of this is outside of our experimentation and outside of the equation within this. So what we can play around with is the environment around that, the entropy of the environment, the temperature of the environment, all of those additional levers that we saw within that equation. We can pull those levers, but let's first get a baseline, right? Let's just see what happens if we're just doing that compression. We're just collapsing the model, like exactly as is predicted within that paper, the physics of that paper, right? And then so we do that, and I do it for 50 epochs in this instance. And then to me, it's kind of important to do it for more than 10 epochs, because you get a lot deviant behavior, especially in these instances, after a lot of epochs, essentially. And then what we notice is that this the model is actually learning in this environment. If you're looking at this test and it doesn't mean much to you, that's like these numbers. That's what these numbers mean. As long as they're going down, it's good, right? So if it starts off in 4.8 and 5.2 range, and then we're ending at the 3.2 to 3.8 range, bravo, very good, very nice. That's what we want to be, right? As long as it's going down. And then what we're showing and what we're demonstrating within this, the hypothesis is, and I haven't run it for more, but this loss is continuing down. and I know someone that has run this particular experimentation with this particular setup, and then according to them, like this model will learn forever in this environment. Like they just stopped because training a model on this because they stopped wanting to pay to train the model. But like they trained like 100 million parameter model using this, right, like this collapse training and collapse compression to train a very small and very tiny model to on a specific task to compete with GPT-4 and large models. And then they utilized GPT-4 as the judge of the outputs. And then so they would give it like, here's your own outputs, and then here's the outputs of our 100 million parameter model, and here's like outputs of Claude, or etc. And 9 times out of 10, GPT-4 would judge the 100 million parameter model as the best one, and just by doing a lot of this, like as much as you want, because as you can see, I mean, if you go through this data, it's not like there's no plateauing, right? Like there's no point where it's steady, and which means that it's not learning. So there's always some sort of interaction going on within this, which proves the physics paper that we were just looking at, that this compression and this model compression is, and in this instance sparsity pruning, is a big deal, and it leads to actual learning, which is very counterintuitive, right? We can prune a model, shrink its parameters down, and then utilize the physics from that, the compression that occurs from that, to actually make the model better. Fascinating, right? So let's dive into the next experiment and then play around with that a little bit more. So that's our base experiment. So now let's start trying to take it off of the rails. So let's we have our base experiment, which is all the same, right? So we have our compression, and then we have our surge, but then let's put in a few measurements here. Let's measure the entropy of the environment and the targets, and then let's within our training loop, let's add a bit of noise to try to increase entropy within the environment is the goal within that noise. So if you go back to this paper, right, one of the things within this is that this H, right, H is entropy of the entire data set, and this is a constant. And then so the entropy of the entire data set is a constant. But what is not a constant is the entropy of the entire digital environment, right? And then so that's what we're playing with in this, is the entropy of the environment. And then so let's do a little bit of playing around within that, and then see and adjusting, and we can see and measure what our average entropy is within the environment. And what our goal is to, with this experiment, is to stabilize entropy within the environment around that 5.5 range, and then see what happens just by doing. So we're doing the compression like we did before, but we're stabilizing entropy. We're introducing an external force to this digital jar to stabilize the entropy of the environment. And then so again, we start off around 5, right? So 5. And we go down and we end about 4.3 in this instance. So what we see is that by stabilizing entropy in this instance, we've actually reduced the loss rate, which is interesting to me, right? So by introducing an element of stability by trying to increase the stability of this chaos that we've created for this model in this environment, we're actually making it learn slower than by just putting in the chaos. Like just the chaos alone is better than this stabilization that we're doing here. But that doesn't mean that stabilization overall is bad, right? So it's just in this instance. So let's play around with it more. Kind of counterintuitive results to what we expected, but let's play around with it more and let's add more stability and more levers within this environment. Remember, like this equation gets us access to a lot of levers, right? So let's play around with some of the levers that this equation is giving us access to. And we'll essentially build out, we'll add more noise into our equation, and then we'll also add a forward pass, and then we're going to do kind of a dynamic surge and a dynamic collapse within this. And then so we're going to introduce the concept of energy and entropy pumps as I introduced at the top. And then so we're going to essentially just pump in energy and entropy and kind of like create like when this collapse happens, we're going to like essentially add an energy bomb and see what happens with that, right? And see how that changes the dynamics of this. And then we're going to do that, and then we're going to also vary the noise and the entropy of that environment. So again, we mentioned that the lever that we have is not data entropy. So the entropy of this is whatever it is for the data set, but we can control and add on top of that, kind of manipulate it via the environmental noise, right? So that's what we're doing is we're testing like environmental noise in this instance translates to injecting different entropy levels into the environment. Like that's kind of a backhanded way of how we're doing that. And then so when we do that, what we can see is very interesting patterns emerge, right? And then so by introducing a little bit of loss, and I only do this for 10 epochs through these. If I were doing this for 50 epochs, this loss would start to go down. So I want you to ignore the loss within these experiments. There's a reason why I do the top experiments at 50 epochs, and then we're only looking at 10 here. I'm only looking at 10 here just because of compute. I didn't want it to take forever because I'm doing a bunch of tests in this run. So what we can see is that entropy does go down a little bit over time. So we are stabilizing, but we're not 100% stabilizing entropy in this instance. But we're doing a solid job of stabilizing total environmental entropy of the environment. But so we're not making this environment as stable as we could. And then that's what we show, right? And that's what the data shows here is that essentially in this instance for these first 10 epochs, this model is just operating in a very stable environment overall. And that's what we see here. These metrics, while it's like you see it jaggy and zigzagging here, we can see that it's just stabilizing, right? It's trying to figure out and learn what's going on in this environment. And then if we extended this out over 50 epochs, this loss rate would smooth out, it would go down a lot more, right? And then so that's why I want you to ignore the loss rate on these experiments. And then so let's do it and let's adjust that noise level. So that first one was 0.05 noise. Let's adjust it. Let's increase the noise a little bit more. And then so what we can see is by increasing the noise a little bit more, we get unexpected results with regards towards the entropy, right? We start to see more and more entropy stabilization of the environment. It's what is essentially occurring here, right? And then that messes with our loss rate very significantly within the first 10 epochs. And then same thing here, right? Even more entropy stabilization in the environment by increasing more noise, which increases disruption of our model over a short time period as well. And then so kind of if we're looking at and we're measuring this over short time periods, what you'll see within this is data that will lead you in the wrong direction, basically. And so that's why I'm trying to highlight and point this out, right? You can see here, this is with no surge and no collapse. But you can see right around here towards the end, right? This is where you start getting into entropy collapse. And then this is what happens in a standard environment, right? So this all looks amazing. And then if you're just measuring this for 10 epochs, you're going to say, hey, this guy's going to win right here, right at 9.5, where you're cutting it off, this monster is looming, right? And then you don't this is cutting off what's happening after that monster. And then what happens after that monster is that these start to win. And so just highlighting that before we go on to the next experiments. So now we did these experiments to understand, right? So can we actually control entropy in the environment? Can we move that lever by injecting noise into the environment? Can we that secondary lever, that secondary entropy lever? And we can. So now that we can do that, let's play around with it, right? Let's go for the extreme and then essentially try to utilize all of these concepts in combination. So we have, at this point, we have access to and knowledge of environmental entropy and entropy pumps, energy pumps, this collapse mechanism, this surge mechanism, and then we can also have control over the dynamics of when exactly we put those surges in those collapses. So we can play around with the dynamics of that, twist it around, right? Like, so we can do like, when we have the collapse, we can introduce an energy bomb right away, and then perhaps suck out some of the energy halfway before the second collapse, etc. Right? And then just play around with the physics until we dial that, right? And then we can put like dials and checks within the environment so that it auto does this as well, right? So then once we figure out what we want our dials to be, we can do that. And that's what all this code is really doing here within this. And then so what we're doing is we're introducing the concept of the entropy stabilization and wanting the model to stabilize entropy within the environment, even though we're collapsing the weights, right? So essentially, going back to this chart, you see this, like this monster here that is looming. Our goal is to avoid the monster, right? We know this is going to happen because this is physics, and then so we want to create a digital environment where we can avoid this physics situation from occurring, and we can do that because it's a digital environment. We can do whatever we want. So we take our digital environment. And that's exactly what we do, right? So we have stabilized entropy in this environment, even though we are creating a situation which is going to lead to entropy collapse over time via this compression that we're doing to these collapsed weights, but via these external entropy pumps that we've introduced to this environment and these energy bombs that we kind of plop in there over time, we get stabilized entropy here. So we can see entropy is high, and then in this instance, what we end up doing as well, just so you know, within this code, is that compression mechanism. Remember, when we're doing that compression, we know that the compression is essentially releasing entropy from the environment is what's happening, right? Like it's taking the entropy that's in the environment and it's compressing it. Law of thermodynamics is that entropy doesn't go anywhere. You're just compressing it, right? But so we can know that and we can do that. So if we have situations where entropy is starting to get high, where it's going to lead to runaway entropy, which will lead to entropy collapse, before we get runaway entropy, compress it, and that relieves and reduces the entropy in the environment. And then so we utilize that compression mechanism itself as environmental stabilization. And then so by doing that, we essentially get stabilized environment. So essentially what we're proving in this test, and we get through here, is one instance away from a self-stabilizing model. This model isn't self-stabilizing because we go through the code and then we go through all the epochs and blah, blah, blah. It's going to take a long time here to go through, but it's not learning very efficiently. It's learning, but like not very well, right? We ran this through for a lot of epochs, like for 10 epochs and 156 total steps in this instance, and we proved that we're able to like really stabilize the entropy over time. So you can see like given a long enough timeline, the entropy is going up in the environment, right? It's going up, I mean, severely slowly. Like it starts off, let's call it like, what would that be, like 3.20, and then by the end it ends at like 3.24 after 10 epochs and 156 steps, but it is going up, right? So after 100 epochs, if that's scaling linearly, it's like you're like maybe all of a sudden up above, like up to like 3.5, and then you start getting like Eventually you'll get high enough entropy to lead to runaway entropy and collapse in this environment. But it's like, I mean, this is as stable as you can get for training purposes. Like, we're not going, like, this environment won't run out of stability for any intents and purposes of training a neural network within this environment. So now we have that established as our baseline. Let's take it to the next level, and we want to essentially make the ultimate model. Right? We want this model to, it's going to compress the weights and collapse, and we're going to utilize all the mechanisms of that, and then we're going to utilize everything that we've learned about entropy, energy, and all of this, and all the mechanics of this equation, and we're going to put it together, and our goal is an ultimate model that, like, essentially, like, self-corrects and learns in this environment more efficiently than any other model. That's the goal, right? And then so we do that via our, we have our, anytime that entropy gets high, we have our collapse, but then we're also introducing the energy bombs in this instance, right? So we go through, and then we start off epoch 1 and epoch 2, so about 6, and then it's 7 at epoch 2. But then look at this, it gets very beautiful. And then by epoch 50, where, I mean, the extreme loss rate at this point, right? So we go from a 7 to 0.05, which is, like, I mean, it's beautiful, as good as you can get. And then we can see entropy is stabilizing in this environment, like very, very stable in this environment, right? We kind of like fixed that issue of it even increasing a little bit over time, or like where, like, this is just like as stable as it gets, right? So just summarizing all of these experiments overall, we're essentially, what we looked at and what we've gone through here is kind of like surge collapse entropy dynamics and all of experiments surrounding this. All of these experiments are directly related to the paper that we looked at, which is playing with the IC physics laws by leveraging digital physics and the principles to optimize neural network learning. And then if you want to dive deeper into this, I give you essentially like a rundown and a description of each one of these experiments, what we went over, and how exactly that they work. So if you like this type of content, please like and subscribe. Hopefully this gives you a little bit of food for thought with regards towards digital spaces, the physics of them involved, and what you can do with those physics. Thank you very much.